All right. Well, welcome to the part 2 or the second lecture about isotonic solutions. And we are going to pick up where we left off. And I'll remind you that means we finished where we were able to evaluate the tonicity of various solutions using either the freezing point depression or the sodium chloride equivalent method. What we're going to do is do a brief review on those skills and then take them further and actually apply them to being able to formulate prescriptions for isotonic solutions. So with that, let's get started. The first question, though, is a review of what we had completed at the end of the part 1 in this lecture on isotonic solutions. So let's read the question. It says, what is the tonicity of a 0.2 molar mannitol solution? And again, mannitol has a molecular weight of 182 and an E value of 0.18, and it is a non-electrolyte. So we want to know what is its tonicity with respect to body fluids. And we're going to use both the freezing point and the sodium chloride equivalent method to do this. So in the end, we want to know, is this 0.2 molar solution of mannitol, is it hypotonic, is it isotonic, the same as biologic fluids, or is it hypertonic? All right. And we're going to do this two ways. Before we split, though, into the freezing point depression or the sodium chloride equivalent, let's convert our units of the 0.2 molar to something we can use within our formulas. So our first step would be to convert the 0.2 molar of mannitol and re-express that as 0.2 moles per liter, since that's what molar is. And since it's 0.2 moles per liter, what we can do is multiply that, and to convert it from moles to grams by multiplying by the molecular weight. So we'll set it up as times 182 grams per 1 mole. That way the units of moles cancel, and 0.2 times 182 gives us the fact that this 0.2 molar solution, or I should say concentration, is the same as saying we have 36.4 grams per liter. All right, so we're going to go forward with that number, and you'll see where that's a more useful number to use in our equations. So let's start with the freezing point depression method. So this formula is the one you should have remembered or have hopefully memorized from the part 1 about isotonic solutions, and that is the fact that we can use this formula to calculate the freezing point depression caused by a solution of a chemical by putting its molecular weight in grams per liter in the numerator of a fraction. So 182 is the molecular weight of mannitol in the units of grams per liter, and we divide that in the denominator by the negative 1.86 degrees Celsius times its dissociation factor I. And since we're talking about a non-electrolyte here for mannitol, we talked about in the last lecture that those have a dissociation factor of 1. So we have the negative 1.86 times 1. We set that equal to the target concentration. In this case, our concentration is 36.4 grams per liter, and you can see why we had to convert it to those units, so it matches the molecular weight units for the mannitol. So both sets of concentrations are in grams per liter, and we then divide that desired concentration by the freezing point depression caused by that concentration, which we don't know, which is what we're solving for, which is why we'll put X there. So X represents the freezing point depression caused by a concentration of 36.4 grams per liter of mannitol. Now when we solve for X, so we take our negative 1.86 times 1 times 36.4, then divide that by 182, you should get numerically the answer of negative 0.37 degrees Celsius. Okay, and that's our answer in terms of the freezing point depression caused by mannitol. Now we need to evaluate that number, and this is the other thing you need to memorize, we emphasized in the last lecture, is that an isotonic solution freezes at a negative 0.52 degrees Celsius. So to compare and determine tonicity, we have to compare our value to the negative 0.52 degrees Celsius for isotonic. Since our value for mannitol, this concentration of mannitol is negative 0.37, that value is less than or I mean, in one sense, it's a greater number then. It's not nearly as negative, but it is a smaller decrease in the freezing point than an isotonic solution. So we would conclude that this has fewer particles and this is a hypotonic solution compared to biologic fluids. So our final conclusion is that this concentration is hypotonic based off of the freezing point depression method. All right. Now, let's do this. Let's say we didn't know that. Let's do this same analysis, but using the sodium chloride equivalent method. Okay. Our first step in this, and you can do this a couple of ways. I think the easiest way is to convert our concentration of 36.4 grams per liter and re-express that into grams per 100 milliliters. And you'll see why here in a little bit. So really, if I just set up 36.4 grams over 1 liter, that's the same as 36.4 grams over 1,000 milliliters. So to get that down to 100 milliliters, I need to divide the top and the bottom by 10. So essentially, an equivalent concentration would be 3.64 grams per 100 milliliters. Okay? So what we're going to do is take that number and compare and use the E value. So we were given the E value for mannitol at 0.18. Another important thing to say to memorize from the last lecture was when we give you an E value without any units, it's very important that you're able to put units with it. So an E value of mannitol for mannitol of 0.18 means that mannitol has the equivalence of 0.18 grams of sodium chloride per 1 gram of mannitol. That is, 1 gram of mannitol produces the same osmotic force as 0.18 grams of sodium chloride. Now that we have that relationship, we can convert the amount of mannitol that we have in 100 milliliters, which we calculated to be the 3.64 grams. So we're going to take that, multiply it by this relationship, this E value, such that we have 0.18 grams of sodium chloride on top over 1 gram of mannitol on the bottom, so that the grams of mannitol cancel. And we can see when we do that math, our final result, our number is 0.66 grams of sodium chloride. Okay, so there we have it. What does that mean? Why did we express this in the amount of sodium chloride equivalent for mannitol that would be present in 100 milliliters? Because what we know for sodium chloride is that an isotonic solution is 0.9%. That means 0.9 grams per 100 milliliters. Therefore, if this solution were to be isotonic for mannitol, it would have an equivalent of 0.9 grams of sodium chloride. However, what we calculated was 0.66 grams of sodium chloride. And since that value is less than what we would have required for an isotonic solution, being 0.9 grams of sodium chloride, we can conclude, again, using the sodium chloride equivalent method, the same conclusion, that this concentration of mannitol, the 36.4 grams per liter, which again is the same as the 0.2 molar concentration we were told to begin with, that concentration of mannitol is a hypotonic solution. So those two were very fundamental skills, both the freezing point depression method and this sodium chloride equivalent method, for at least at this point evaluating the tonicity of a solution. Now, let's go a little bit further here and answer this question, because it asks now, well, instead of evaluating a current concentration, what we want to know is what concentration, that is what percent weight per volume concentration of mannitol would be isotonic. So we know the 0.2 molar in the previous question was hypotonic. Now, how could we do the same thing by just asking the question, well, what concentration of mannitol is isotonic? And we're going to answer that question again using both the freezing point depression and the sodium chloride equivalent method. So let's start off with the freezing point depression method, and we're going to use that same formula that's set up very similarly to begin with. If you look on the left-hand side here, it's the same setup because the molecular weight of mannitol is still the same. It's 182. So we set the molecular weight in grams per liter on top, so 182 grams per liter in the numerator. Divide that by the negative 1.86 degrees Celsius times the dissociation factor, which again, for mannitol being a non-electrolyte, we'll use the number 1. What's different now is on the right-hand side, we're going to set that equal to, what we're solving for now is the concentration. We want to know the concentration that's isotonic. So our concentration is unknown, so we're going to put X in the numerator. But in the denominator, what we do know now is the freezing point depression we want, because we know an isotonic solution freezes at negative 0.52. And that's the concentration I want to find, is the concentration that produces a negative 0.52 degrees Celsius depression, because that would be isotonic. So if we solve for x, we would take our 182 times a negative 0.52, and then divide that by a negative 1.86, and our answer, our result rounding a little bit for x, would be 51. And remember, x represents the concentration of mannitol that would be isotonic in the units, though, of grams per liter. So below that in this formula, you can see I say x equals 51, which was our numeric answer, but I now put the units of grams over 1 liter. That's important. I just wanted to do that, express my answer that way, because again, the question wants to know what percent weight per volume concentration of mannitol. So I know the correct answer is 51 grams per liter, but that's not the correct final answer. So what I'm showing you here is I'm just re-expressing the 51 grams per liter by saying that's the same as 51 grams over 1,000 milliliters. And to convert that to a percent, which is per 100 mils, I need to divide the top and the bottom by 10. So again, that is equivalent to 5.1 grams over 100 milliliters. And since that's in grams per 100 milliliters, that's the same as percent. So essentially, an isotonic concentration of mannitol would be a 5.1% weight per volume solution. And we solve for that and determine that in this sense using the freezing point depression method. Okay, so now let's see if we can come up to that same answer essentially using the sodium chloride equivalent method. To do this method, the first step I would tell you to do would be to calculate how much sodium chloride we would need to have an isotonic solution. So that's kind of by default. We remember that 0.9% weight per volume sodium chloride is isotonic, meaning 0.9 grams per 100 milliliters. Therefore, we need enough mannitol weight that would be equivalent to 0.9 grams for the 100 milliliters. Okay, we look up above and we see the E value of mannitol is 0.18. I'll remind you that means 0.18 grams of sodium chloride per 1 gram of mannitol. So we go down to the bottom line, you can see. Let's take our target for sodium chloride, which we said was 0.9 grams for every 100 mils. Multiply that by the E value expressed as 1 gram of mannitol on top over the 0.18 grams of sodium chloride, so that the units of grams of sodium chloride cancel. And when we do that math, we take 0.9 times 1 divided by 0.18. We get, rounding here a little bit, to the value of 5. And the units would be grams of mannitol. That means that we need 5 grams of mannitol for every 100 milliliters to make an isotonic solution. 5 grams over 100 mils means we need a 5% weight per volume solution. So again, we essentially came to the same answer using both the freezing point depression method on top as well as the sodium chloride equivalent method on the bottom. All right. Now, that was enough review, and those are still some fundamental skills we're going to use. But let's now approach this, that how are we going to actually determine the amount of, how do we create prescriptions for isotonic solutions when we also have drugs in them? Because the drugs, the active agent, the reason we're trying to compound this product, will produce some effect on tonicity itself. So we're going to have to account for the osmotic effects of the drug, but very often we're going to need to add another substance to make up the remainder of the tonicity to make a final isotonic solution. So remember, drugs and their tonic effects have to be combined with another inert substance with its tonic effects, so that in the end you have a overall isotonic solution. So hopefully that made some sense. I'm sorry. Now, there are two methods of doing this. We are going to learn how to do this both using the freezing point depression method and the sodium chloride equivalent method. So let's focus first on this procedure for the freezing point depression method. You know a lot of this already. Remember, with the freezing point depression method, we want our solution to essentially freeze at a negative 0.52 degrees Celsius. If our combination of drug and inert substance freezes at that temperature, then it's isotonic. All right? What we'll need to know then is our active agents will have to be able to know the change in freezing point that drug causes so that we can account for that. Oftentimes you'll use these tables, and there's a table on the right-hand side is straight out of the textbook, and they'll report the freezing point depression of various solutions they standardize it in a 1% solution. So for example, on the table here, all of these numbers, like for example, atropine has a value of 0.7. What does that number mean? The 0.7 represents the change or the decrease in freezing point produced by a 1% solution. Okay? So they will usually express that as what we call a delta for a change sign. So the Greek letter delta, capital T for temperature, a little f for freezing, and then a 1% to represent that this value is the value produced by a 1% concentration of that solution. Okay? So delta TF, 1%, represents the change in temperature produced by a 1% solution of that drug. Okay? Or that chemical. So that's important. With that information for whatever our active agent is and for also whatever our inert agent is, we can use that information to formulate our prescription. We would do that by first determining the freezing point depression caused by our active agent. Remember, the concentration of our active agent will be the concentration it needs to work therapeutically for whatever condition we're wanting to treat. So based off of its therapeutic concentration, we'll determine the freezing point caused by that amount of drug. Okay, we will subtract that freezing point depression from our target, which was the negative 0.52. So we'll determine the difference that we still need to obtain from another substance. And then from that freezing point depression that we know we still need to get, we will determine the weight of this additional or non-active inert substance needed to produce that freezing point depression. Okay, pretty straightforward. That's how you would approach it using the freezing point depression method. Now, before we practice these problems, let's make sure we would know how to accomplish that same thing, but using a sodium chloride equivalent method. And as a reminder, the whole way this system works is the fact that we know that sodium chloride produces an isotonic solution at a 0.9% weight per volume. We also can look up tables like shown here on the right that include for us, for a variety of different substances, their E value. We could go to the effort, and we learned in the first lecture actually how to calculate the E-value, but in this case, we're not going to spend all that time again calculating E-values when there are tables that report E-values for a variety of different substances, so we can just use those E-values. Okay, to do this. So how would we start with this? Well, the first thing we would do is use the table here and actually calculate the equivalent amount of sodium chloride contributed by each of our active ingredients at whatever concentration they need to be in the solution to work therapeutically. So again, this could be for multiple drugs or a single drug, whatever drugs we have that we need therapeutically. Based off of their concentration, we use the E value to determine their relative contribution of a sodium chloride equivalent. All right, so we know how much equivalent sodium chloride is coming from all of our drugs. We then, based off of whatever volume we're compounding, determine the amount of sodium chloride we would have needed of pure sodium chloride to make it isotonic. Since we know the solution has to be 0.9% sodium chloride to be isotonic, we can determine our target amount of sodium chloride. Once we know that target amount, we subtract the amount of sodium chloride coming from all of our active ingredients, and whatever is left, this difference, is the amount of sodium chloride that needs to still be added to the solution. What's interesting in this method, like I talks about in step 4, we could always just use sodium chloride to make up the difference. So in there, you don't have to use E values, you just use the concentration of whatever sodium chloride additive you're using and determine the amount to add. Or you can use something other than sodium chloride to make up the difference in sodium chloride by using an E value for whatever you're using, boric acid or whatever other inert ingredients you want to use. It has an E value. You can use the E value to determine how many grams of the drug or that inert drug you would need to provide the amount of sodium chloride left. So step 4, I don't know if I explained that well, but remember step 4 in the sodium chloride equivalent method allows you to either use sodium chloride or some other drug, whatever you want, to make up the remainder of the sodium chloride equivalent that you need to make the solution isotonic. All right. Better than a description would be some worked sample problems. So let's just put this into action. And we are going to do some of these same prescriptions in both freezing point and sodium chloride equivalent methods. So let's start with this first question that says, How many grams of sodium chloride should be used in compounding the following prescription? Okay, and the prescription calls for using hydrous dextrose at a concentration of 2.5% weight per volume. So we're going to have a certain concentration, 2.5% of dextrose, and then add an additional amount of how much ever you need of sodium chloride. So we're going to QS with sodium chloride and sterile water to make a final solution that has 100 milliliters. 1,000 milliliters. So this 1,000 milliliters needs to be isotonic, but whatever it's part of that contribution of the isotonicity will be from the 2.5% concentration of dextrose. All right, and we're going to first accomplish this by using the freezing point depression method. All right, so the first thing we would need to know then would be the reduction in freezing point caused by our ingredients, and our two ingredients are dextrose and sodium chloride. So we would go back to our reference source and look for the delta TF 1% values. And what we see for dextrose, its delta TF 1% is equal to 0.09 degrees Celsius. So a 1% solution of dextrose lowers the freezing point by 0.09 degrees. Well, what is the value for sodium chloride? We look up the sodium chloride and get a value of 0.58, meaning that a 1% solution of sodium chloride would reduce the freezing point by 0.58 degrees Celsius. So using those two factoids, we can now go ahead and determine the relative amount of sodium chloride we need. The first step to do that, though, remember, is we know that we need an exact amount of dextrose. We need 2.5%. So let's start by figuring out how much reduction in freezing point will be caused by the amount of dextrose in our solution. So remember, we have a value, a delta TF 1% value for dextrose, and it was 0.9 degrees Celsius. So the first thing we'll do on the left-hand side here, you can see, let's set up that proportion or that relationship. We know from the textbook that you get 0.09 degrees Celsius reduction with a 1% concentration of dextrose. We then set that equal to some unknown X value, which is we don't know how much of a change in temperature we're going to get, but we're going to set that over the fact that we do know what we're going to compound is going to have exactly 2.5% dextrose. So we'll be able to use this proportion to determine if I have 2.5% dextrose, how much change in temperature do I get? Because I do know that with a 1% concentration, I get a change of 0.09. So those are the proportions we're using. So now, going back on top, if we solve for x, we would take 0.09 times 2.5 and then divide by 1 in this case. So if we solve for x, we see that a 2.5% concentration of dextrose would reduce the freezing point by 0.225 degrees Celsius. Okay? Good. Now, but that's not where we need to be at. What does our final reduction in temperature need to be? Remember, for isotonic solutions, it needs to be 0.52 degrees. Okay. Now, I'm getting rid of the negative sign here. We could do all of this in negative, but we're doing kind of absolute values here. We need a total change. In this case, it's a reduction, but a total change down to 0.52 degrees. So from that target of 0.52, I'm going to subtract the amount produced by our dextrose, which we just calculated to be 0.225. So when I subtract that, I see that I still need to obtain, the difference between those two is 0.295 degrees Celsius. All right? That's the amount of reduction in temperature I still need to obtain. What am I going to use? What is going to provide enough particles to be able to have that reduction in temperature? Sodium chloride. And I can add as much as I need till I get that change in temperature. Okay? Since we saw on the table, the delta TF for sodium chloride for a 1% solution was 0.58. Let's set that up as a proportion. So we have 0.58 degrees Celsius on top over the 1% sodium chloride solution that causes that. Set that equal to. Now we know the target change in temperature. What we want is whatever concentration of sodium chloride gives us a reduction of 0.295 degrees Celsius. So we put 0.295 on top and set that over X. And here X will represent the concentration in percent of sodium chloride that produces the amount of decrease in temperature that we want. So if we solve for X, we would take the 0.295 times 1 and divide it by 0.58. And when we see that, rounding a little bit, we can see that we solve for X, that equals 0.5% sodium chloride. Okay? The only trick at this point, so that's what we know, our 1 liter bag that we're going to make needs to have 0.5%. Okay, so we need to solve, though, for the weight of sodium chloride, because it wants to know how many grams. That's the question refers to. So let's take our 0.5% and set that as a proportion, saying that 0.5 grams of sodium chloride over 100 mils, since that's what 0.5% represents, let's set that equal to some X grams of sodium chloride per 1,000 milliliters. And you can certainly solve for this a couple of different ways. But 0.5 times 1,000 divided by 100, solving for X, would give you a total value of 5 grams. So this says we need 5 grams for every 1,000 milliliters to make a solution that has 0.5% sodium chloride. Because when you add that amount of sodium chloride to a 2.5% concentration of dextrose, the final combination of both the dextrose and sodium chloride produces the same amount of osmotic force, has the same number of particles as a isotonic solution, which is what we were trying to solve for. Now let's solve the same problem and compound the same solution, but use the sodium chloride equivalent method. So it starts off very similarly like we did for the freezing point depression method, where we had to look in a reference there to find the delta TF 1% values. Here, we need to look into a reference and find the sodium chloride equivalent methods for our ingredients. Okay? In this case, so I want to point out you got to be a little bit careful with dextrose, because there are different entries when it's anhydrous dextrose versus hydrous dextrose. Okay? So we can see up on the prescription here that what we're using in this formulation is the hydrous form of dextrose. So we go down to the dextrose with the water, the H2O. We go over to the far right, and we can see that its E value, its sodium chloride equivalent, is 0.16. So that's the value we will use, is the value for the hydrous dextrose, not the anhydrous. All right? So let's set this up. First thing we would do is calculate the amount of dextrose that we will have in our solution, because we know we're compounding 1,000 milliliters. That's going to be 2.5% dextrose. So we'll start with 1,000 milliliters, multiply that times 2.5 grams of dextrose per every 100 milliliters. That's 2.5% weight per volume. The units of milliliters cancel, and we would get a final answer of 25 grams of dextrose. That's how much dextrose will be in our 1,000 milliliters. Now, let's determine how much sodium chloride equivalents that amount of dextrose produces. So let's take our 25 grams of dextrose and multiply it by its E value, expressed as 0.16 grams of sodium chloride in the numerator over 1 gram of dextrose in the denominator, so that the units of dextrose cancel, and we take 25 times 0.16. Our numeric value is 4, and that represents 4 grams of sodium chloride. So essentially 25 grams of dextrose produces the same osmotic forces as 4 grams of sodium chloride. Okay? Now we'll compare that to our target, and what we know our target to be is 0.9% weight per volume, which is 0.9 grams for every 100 milliliters. But since we're trying to compound 1,000 milliliters, let's multiply both the numerator and denominator by 10. So we can see that our target is 9 grams of sodium chloride for every 1,000 milliliters. So let's take our target of 9 grams, subtract the amount of sodium chloride we're getting from our dextrose, and you can see that our final answer, like it was for the sodium chloride equivalent method, for the freezing point depression method, is 5 grams. So we calculate that we need to add 5 grams of sodium chloride to the 2.5% dextrose to get essentially a final isotonic solution. All right, well, let's move on to a different prescription. So we've just looked at compounding an IV solution. So let's transition to looking at an ophthalmic solution, an eye drop. like IVs, we still want our ophthalmic solutions to be compatible with our biologic tissues. We don't want to cause irritation in the eye, so we want our final ophthalmic solution to be isotonic so that it's compatible with lacrimal fluid and, again, doesn't cause any eye irritation. In this situation, well, let's read the question. It says, how many grams of boric acid should be used in compounding the prescription? And so the prescription is for homatropine hydrobromide, 1.5% weight per volume solution, and to make it isotonic with boric acid, such that we have a final volume of 20 milliliters. So homatropine hydrobromide, the therapeutic agent, is used to cause mydriasis, or dilation of the pupil of the eye, so that a doctor or ophthalmologist can look inside the eye for some sort of condition or issues. So we want to dilate the eyes so that they can be examined, and that's what we'll use the homatropine for. But clearly, probably the homatropine at the therapeutic concentration we need, the 1.5%, is probably not going to make the solution itself isotonic. So we need to add additional boric acid so that the final product is isotonic and won't cause any eye irritation. So the first step, and just realize, in this question, we also are told we want to use the freezing point depression method. So with the freezing point depression method, first thing that you're going to need to do is go to your resource and look up the delta TF 1% for each of your ingredients. And so our therapeutic agent is the homatropine hydrobromide, and we can see that its freezing point depression is 0.11 degrees Celsius. And we would also need to know it for the boric acid, the inert agent we're going to use to essentially adjust the tonicity. And so its delta TF is 0.29. Now that we have that information, we can go ahead and start to work on our calculations. So on the top left over here, let's start with the homatropine, and let's determine how much of a reduction or depression in the freezing point the required concentration, the 1.5%, will cause. And we'll start that by using the delta TF 1% that we looked up and set it up as a proportion and say that we get 0.11 degrees Celsius reduction when we use a 1% concentration of homatropine. That's the value we looked up. Set that equal to some unknown change in temperature over when we use our required concentration, which is 1.5% homatropine. So if we solve for x, we would take 0.11 times 1.5 divided by 1. We see that numerically we get 0.165, and the units would be degrees Celsius. So the 1.5% homatropine will reduce the freezing point by 0.165 degrees Celsius. The next question to ask is, okay, how much freezing point depression do I still need to get? So let's take our target, which we said for an isotonic solution is 0.52 degrees Celsius. Let's subtract the amount we're getting from the homatropine, which is the 0.165 degrees Celsius. We find the difference, and we see we still need to get 0.355 degrees Celsius reduction in freezing point. How are we going to get that? We're going to use boric acid. So let's use the delta TF that we looked up for boric acid and set it up as a proportion and say that we get 0.29 degrees Celsius reduction when we use a 1% concentration of boric acid. Let's set that equal to the amount of freezing point depression we need, which is 0.355 degrees Celsius over x. And now when we solve for x, we will determine the percent concentration of boric acid required to get that reduction in freezing point depression. So if I take 0.355 divided by the 0.29, my answer numerically would be 1.2, and that represents 1.2% weight per volume of boric acid. That's the concentration of boric acid that gives me my desired reduction in freezing point. The only last step is the fact that, well, I got 1.2%, but I need to know the actual grams of boric acid to make my 20 milliliters be 1.2%. So let's set up the proportion of 1.2%, meaning 1.2 grams of boric acid for every 100 mils. Set that equal to x over 20 milliliters. Solve for x by taking 1.2 times 20 divided by 100, and we see numerically the answer is 0.25, and the units would be grams of boric acid. So what I know now is that if I use 0.25 grams of boric acid along with the required amount of homatropine, and I QS up to a total volume of 20 milliliters, it would have the total amount of osmotic forces to equal biologic fluids, which means it would be isotonic, and that essentially answers this question. All right, let's solve this same problem, figure out how much boric acid we need, but let's base it off the sodium chloride equivalent method. So like the freezing point depression method, the first thing we needed to go to is our reference sources. But now what we need to look up are the E values, the sodium chloride equivalent values for our two ingredients, that being the boric acid and the homatropine. So as you can see on this table here, we see that for boric acid, it has an E value of 0.52. And then for the homatropine, it has an E value of 0.17. So we'll need to use those numbers in our calculations here in a minute. What is different about this method from the freezing point depression method, where we were able to do everything as a percent concentration until the very end, now what we need to do is we need to start with the homatropine, but we need to get it out of the percent weight per volume concentration and actually figure out how many grams of homatropine we're going to need. So our first step is to do that. And when we would do that by starting with the fact that we are going to compound 20 milliliters. That's the volume of our ophthalmic solution. That solution needs to be 1.5% weight per volume homatropine. So we'll multiply our 20 milliliters times its concentration as 1.5 grams of homatropine for every 100 milliliters. That's its percent concentration. And if we multiply that, milliliters cancel, and we see that our answer would be 20 times 1.5 divided by 100. The number would be 0.3, and that's grams of homatropine. So that's how much actual homatropine we need to essentially dissolve in our 20 milliliters to get the therapeutic concentration. What we now need to know is, since we will have 0.3 grams of homatropine, how much sodium chloride would that mimic? How much sodium chloride would that be equivalent to? So let's take the 0.3 grams of homatropine and multiply it by the E value for homatropine, expressed as 0.17 grams of sodium chloride on the numerator over 1 gram of homatropine, so that the units of grams of homatropine cancel and we will have grams of sodium chloride. So if we take 0.3 times 0.17, we see that our numeric answer would be 0.05, and that is in grams of sodium chloride. So what we've determined is that adding our 0.3 grams of homatropine produces the same osmotic forces as if we had added 0.05 grams of sodium chloride. All right, let's take a break, step back a little bit, and say, well, okay, how much sodium chloride total do I need? Well, I know that an isotonic solution of sodium chloride is 0.9%. I know that means 0.9 grams for every 100 milliliters. So let's set that equal to some X grams of sodium chloride over the volume I want to prepare, which is 20 milliliters. So now if I solve for X by taking 0.9 times 20 divided by 100, numerically I would get 0.18, and that would be grams of sodium chloride. That's my target. That's how much sodium chloride I would need to make 20 milliliters be isotonic. So let's take our target of 0.18 grams and subtract the amount of sodium chloride equivalent I'm getting from my homatropine, which we calculated to be 0.05 grams. So I subtract that and see that the difference between those two is 0.13 grams of sodium chloride. That's the amount of sodium chloride I would still need to add to my 20 milliliters to make it isotonic. Now, unlike our previous example for sodium chloride equivalents, we are not going to use sodium chloride to make up the difference. We want to use boric acid. So what I need to do is convert or determine the amount of boric acid that's equivalent to the 0.13 grams of sodium chloride that I need. So let's start with the 0.13 grams of sodium chloride and multiply it by the E value for boric acid, but expressed as 1 gram of boric acid in the numerator over 0.52 grams of sodium chloride. That way the units of sodium chloride cancel, and I get my final answer to be grams of boric acid. So if I take my 0.13 grams times 1 divided by the 0.52, my number ends up being 0.25, and that represents grams of boric acid. So 0.25 grams of boric acid would have the sodium chloride equivalent of 0.13 grams, which is the additional amount of sodium chloride or the initial amount of osmotic forces I need to have to add to my homatropine to give me an isotonic solution when we're completed. And that answers this question, accomplishing the same thing but using the sodium chloride equivalent method. All right. Let's go on to another example here where we'll start with the freezing point depression method. And it says, how many grams of sodium chloride should be used in compounding this prescription? And the prescription calls for naphthalene hydrochloride 1%. That's our therapeutic product. And we want to add enough sodium chloride so that the final 30 milliliters is isotonic. And we're going to use this again as an eye drop to help kind of get rid of red eyes. The naphthalene is a kind of vasoconstrictor to kind of get the red eyes effect out. Okay, so we're doing this starting off again with the freezing point depression method. So let's go to our reference source and see that our two items that are going to be in our formulation include the naphthalene, which is a freezing point depression of 0.16, and sodium chloride, which has a freezing point depression of 0.58. And again, for both of those are for a 1% solution. All right, so let's start with the naphthalene. What we need to know is we know that its delta TF 1% is 0.16, so we get 0.16 degrees Celsius change for every 1%. Set that equal to some unknown amount for what we need in the prescription, which is conveniently 1%. So hopefully this is a pretty easy. I wanted to set it up the same, but you realize since we are wanting therapeutically a 1% concentration, clearly it will change the freezing point by 0.16 degrees. So let's take our target of 0.52 degrees, subtract the 0.16 we get from the naphthalene, and we still need to get 0.36 degrees Celsius change in freezing point. What are we going to use to get that? Is the sodium chloride. So we set its delta T up as 0.58 degrees Celsius for every 1% of sodium chloride. Set that equal to the desired freezing point depression we want, which is 0.36. Set that over x. We solve for x by taking 0.36, dividing it by 0.58, and numerically we get 0.62. And that represents a 0.62% concentration of sodium chloride. All right. So lastly, how much we're not making 100 mils though, we're only making 30 mils. So let's calculate the weight of sodium chloride for our 30 mils. Well, if we want a 0.62% concentration, 0.62 grams for every 100 milliliters, set that equal to x over 30 milliliters. We solve for x, it would be the grams of sodium chloride we need. So we take 0.62 times 30 divided by 100, and our answer would be 0.19. So what we need to add is 0.19 grams of sodium chloride to our concentration of the naphthalene, and we would get an isotonic solution. All right, let's solve this same question now, but use the sodium chloride equivalent method. And like we did with the freezing point depression method, we need to go to our resources and find, in this case, our E value for naphthalene. And we see that that is equal to 0.27. All right. So again, unlike the freezing point depression method where we can do everything in percents until the end, we here need to start off by determining the actual weight of naphthalene in our ophthalmic solution. So let's take our 30 milliliters times its concentration of 1 gram of naphthalene for every 100 milliliters, since it's a 1% weight per volume. We multiply that, units of milliliters cancel, and so 30 divided by 100 equals 0.3, and that would be grams of naphthalene. That's the weight we need. Let's figure out how much sodium chloride that weight of naphthalene is equivalent to. So let's take the 0.3 grams of naphthalene, multiply it by the E value expressed as 0.27 grams of sodium chloride over each 1 gram of naphthalene. Grams of naphthalene cancel, and if we take 0.3 times 0.27, we see numerically we get 0.08, and that would be grams of sodium chloride, meaning the amount of drug we're putting in, the 0.3 grams of naphthalene, is equivalent to, osmotically, putting in 0.08 grams of sodium chloride. So let's stop and figure out, okay, well, what is our target? How much sodium chloride total would we need? Well, we'll go back to the fact that isotonic solution is 0.9%, which is 0.9 grams for every 100 milliliters. Let's set that equal to some unknown grams of sodium chloride over the volume we are trying to compound, which is 30 milliliters. So now if we solve for x, we take 0.9 times 30 divided by 100. We see that numerically we get 0.27, and that would be grams of sodium chloride. That's our target. That's how much we would need to make 30 milliliters be isotonic. So let's take that target of 0.27 grams and subtract from it the amount of sodium chloride we're getting equivalent from our naphthalene, which we calculated to be 0.08. So we subtract those two and find that the difference is 0.19 grams of sodium chloride. So that's the amount of sodium chloride we still need to add to be able to get an isotonic solution along with our naphthalene. All right, well, this is the last question, and I wanted to do kind of a review. We've been so focused on doing the isotonicity calculations that I also wanted to kind of go through and review some of our other normal calculations for concentrations and dosing and things like that. So this will be a little bit of a longer, broader question. So it starts off with this prescription, and the prescription calls for cromolyn sodium, which is something used for allergies. It helps reduce histamine release from the mast cells, so it helps with red eyes and helps with allergies and itchy eyes. So we're going to use cromolyn sodium at a concentration of 5%. We're also going to add benzalkonium chloride at a concentration of 0.005%. All right, it's a low concentration, but benzalkonium chloride is used as a preservative, so we don't need very much of it. To that, we're going to add whatever amount of glycerin that we need, primarily as a tonicity adjuster. Combine that with water and compound up to a total volume of 15 milliliters. So we do want an isotonic solution with a total volume of 15 milliliters. We'll use glycerin to adjust for the tonicity of our two active ingredients. All right. So, first step, it says, how many milligrams of cromolyn sodium should be used to fill this prescription? Right? So it's kind of a concentration question. Well, let's start with the volume we're wanting to prepare, which is 15 milliliters. And we'll multiply that by the fact that it calls for a 5% concentration. Since that's weight per volume, that means grams per milliliter. So multiply that by 5 grams for every 100 milliliters. Milliliters will cancel and will be in grams, but the question wants it in milligrams. So let's also multiply it by the fact that there's 1,000 milligrams for every 1 grams. So the units of grams cancel. And if we do 15 times 5 divided by 100 times 1,000, your final number should be 750, and that is in milligrams of cromolyn. So this prescription calls for us to use 750 milligrams of cromolyn. Second part, it says, how many milligrams of cromolyn sodium is the patient receiving per drop? And how much of the drug is being retained by the eye? And to answer that, you got to know that an average dropper delivers about a 50 microliter per drop. And a blinking eye, keep in mind, there's only a certain volume that can stay in contact with the eye. And we're saying that contact amount is about 10 microliters. Okay? So let's start with the first question, which is how many of milligrams of cromolyn sodium is the patient receiving per drop? Okay, so let's start with the 1 drop. So if we start with 1 drop, we can then convert the drop to the volume of that drop. So let's multiply 1 drop by the fact that we were told that each drop contains 50 microliters. All right, so 1 drop times 50 microliters per drop, the units of drop cancel, and we're in microliters. However, our concentration is expressed in milliliters. So let's get rid of microliters. So I'm going to convert the microliters to milliliters by multiplying it by the fact that I know that for every 1 milliliter, there is essentially 1,000 microliters. So now my units of microliters cancel, and I'm in milliliters. I can then now multiply that by my concentration, because I know my concentration is 5% weight per volume, which means I have 5 grams for every 100 milliliters. The units of milliliters cancel. And then lastly, I need to get my answer in milligrams. So let's convert grams to milligrams by multiplying it by 1,000 milligrams for every 1 gram. And if I do that math all the way from left to right, I should get a numeric answer of 2.5. And remember, the final units are in milligrams. So it's kind of interesting to know that every single 1 drop, based off of the drop size, will be providing me 2.5 milligrams of cromolyn sodium. Okay. Not all of that, though, is going to stay on the eye. So we need to kind of proportion out how much actually just stays in the eye. All right. So, and we can do this, you could do this a couple of different ways. If I kind of go back and do it the long ways, and starting back with the fact that we really know now that only 10 microliters will stay in contact with the eye. So let's just use the volume being 10 microliters. So if I have 10 microliters of this solution, let me first convert that back to milliliters. So 10 microliters times, for every 1 milliliter, there's 1,000 microliters. So the microliters cancel. Let's multiply that by the concentration of 5 grams on top over every 100 milliliters. So my units of milliliter cancel. And then you can also then convert that to milligrams by multiplying by 1,000 milligrams for every 1 gram. So if I do that math all the way across, I can see that 10 microliters, when the end only contains 0.5 milligrams. Okay, so that's the amount that answers that question. And again, you could have proportioned out our answer from above. The 2.5 was for 50 microliters. You could have just divided that by 5. But either way, you can also just go back and solve it this way as well. Next question says, how many milligrams of the benzalkonium chloride and how many milliliters of a 1 to 750 concentration, weight per volume solution, should be used to fill this prescription? Okay, so this is about the benzalkonium chloride, and there's kind of 2 questions here. So let's just do one at a time. The first thing it wants to know is how many milligrams of benzalkonium chloride do we need based on the prescription? All right, so let's answer that first. The prescription calls for 15 milliliters, so we'll start with 15 milliliters, and let's multiply it by its concentration, which we desire to be 0.005%, which means 0.005 grams for every 100 milliliters. So then that gives us the milliliters cancel and we'll be in grams. To convert from grams to milligrams, we multiply by 1,000 milligrams per gram, and we see, if we do the math across, that our 15 milliliters will need to contain 0.75 milligrams of benzalkonium chloride. Okay? The next step is to determine how much of this solution we would need. So let's take the amount that we need, which is the 0.75 milligrams that we just calculated. Let's convert that to grams by multiplying by the fact that in every 1 gram, there's 1,000 milligrams. So milligrams cancel. Now I'm in grams, and I did that so I can multiply it by its concentration. And keep in mind, since it was given to us as a weight per volume concentration, that meant grams per milliliter. So let's multiply it by the concentration expressed as 750 milliliters on top over every 1 gram, so that my units of grams cancel. And if I do that math from left to right, I should get a final answer of 0.563 milliliters. And that's the volume I would need of my 1 to 750 benzalkonium chloride solution to provide me the 0.75 milligrams required by the concentration of the prescription. All right, this last question is to determine how much glycerin we need. It's the last ingredient, so we know our 2 active ingredients and how much we're going to use, the cromolyn and the benzalkonium chloride. What we need to determine now is how much glycerin, and I'll remind you the amount of glycerin is related to the amount that we need to make the final product isotonic. So the only things that we'll need to know is, first of all, I give you the specific gravity for glycerin at 1.25. We'll need that. And again, I'm also told in this question to use specifically now the sodium chloride equivalent, so we'll need to do E values. So the first step is to go to our reference source, but this time I'll remind you we need the E values for each of our ingredients. And even though we're going to be calculating the amount of glycerin we need, the amount of glycerin we need will depend on how much we need to get in on top of the amount contributed from the benzalkonium chloride and the cromolyn. So we see all of the E values listed there from our reference. Once we have that, we can begin to solve this question. And I show all of this work on the left-hand side. Let's start on the top. And on this question, I've also tried to compact my steps together. Since you're an expert after having watched all these examples by now, I'm going to go a little bit faster on how you can combine some of the steps together. So let's start with the cromolyn sodium. And we know we want to prepare 15 milliliters. So if I start with 15 milliliters and multiply by the concentration of cromolyn, which is 5% or 5 grams over 100 milliliters, we can see that milliliters cancel, and we would be in grams of cromolyn. Now I'm going to directly convert to an equivalent amount of sodium chloride by multiplying by the E value, which for cromolyn is 0.11, so 0.11 grams of sodium chloride on top over the per 1 gram of cromolyn on the bottom, so that the units of grams of cromolyn cancel. And my final answer, if I multiply that through, would be 0.083 grams of sodium chloride. Okay, that's the equivalent amount of sodium chloride provided from the amount of cromolyn that will be in my solution. Now, let's do the same exact thing for the benzalkonium chloride. Start with the 15 milliliters. Let's multiply it by its concentration of 0.005 grams of benzalkonium chloride per every 100 milliliters. Milliliters cancel. Now I'll convert that to sodium chloride by multiplying by its E value expressed as 0.16 grams of sodium chloride on top over 1 gram of benzalkonium chloride on the bottom. Grams of benzalkonium chloride cancel. And my final answer now, if I multiply all the way across, it's a pretty small number, but it's 0.0001 grams of sodium chloride. All right, so now I know how much sodium chloride equivalent are coming from my two active ingredients. I step back. I now want to calculate how much sodium chloride I need total by starting with my 0.9%, which is 0.9 grams per 100 milliliters. Set that equal to X over 15 milliliters. Solve for X. I get 0.135 grams of sodium chloride. That's how much sodium chloride I need to make 15 milliliters isotonic. So let's take that target and subtract what we have. So let's take our 0.135 grams, which is our target amount of sodium chloride, subtract the 0.083 grams from the cromolyn, subtract the 0.0001 grams, which comes from my benzalkonium chloride, and what I see that is left that I still need to obtain is the 0.052 grams of sodium chloride. And remember, the whole point of this question was to calculate how much glycerin we need. The amount of glycerin we need is the amount that provides us the equivalent amount of 0.052 grams of sodium chloride. So let's start with that amount, the 0.052 grams of sodium chloride, multiply it by the E value for glycerin, expressed though as 1 gram of glycerin on top per every 0.34 grams of sodium chloride. That way the units of grams of sodium chloride cancel, and now I've calculated the weight of the glycerin I would need. However, I want to determine the volume I'll need to use to compound. So I'm going to use the specific gravity of 1.25, and keep in mind we can treat that like a density since our reference source is water. So I'm going to multiply it by the fact that in every 1 milliliter of glycerin, there is 1.25 grams. And if I put grams on the bottom this way, grams of glycerin cancel. And my final answer as I multiply from left to right numerically would be 0.12, and the remaining units is milliliters. So what I've determined is that I require 0.12 milliliters of glycerin to be added to my weight of benzalkonium chloride, to the weight of the cromolyn sodium, and then I mix all that together and use sterile water and QS up to a total volume of 15 milliliters, and I would have the right final volume, I would have the right final concentrations of each of my drug, and more importantly, with the inclusion of the glycerin, I would have enough osmotic forces with all of those dissolved particles that it would be isotonic with my biologic fluids and not cause any ophthalmic irritation to the eye. So that concludes this question, and more importantly, it concludes this lecture, which really, to sum up, has been the practical application of your freezing point depression and your sodium chloride equivalence skills in being able to determine the quantities of ingredients needed so that the final compounded product, whatever you're making, whether it's an IV or an ophthalmic solution, has the same osmotic forces, or in a sense is isotonic with biologic fluids. So hopefully you found this lecture helpful.